Okay, so let me remember that we have proven the following. So if omega is an open set and U C2 omega and U is harmonic in omega, then we have shown that for any x naught in omega, for any rho positive, so that the ball of radius rho centered at x naught is contained in omega, then U satisfies the mean value property. U of x naught, U y dy. So this condition can be also written as follows: the distance of x naught from the boundary of omega is larger than rho. So we are in the following situation. We have just an open set. Then there is x naught. Then there is the distance between x naught and the boundary of omega. Say in this picture, for instance, say is this. Okay. And then for any ball centered at x naught, this is rho. If I compute the mean value, so this means 1 divided omega n rho to the n integral. This is a notation. This is a notation. So this means exactly this. This symbol means that I divide the integral divided by the volume of the ball. Okay. Another notation that it is possible to find is this. This is U and the y. This denotes the volume of the ball of radius rho centered at x naught. Okay. So for a function U into C2 satisfying this, we have proven the mean value formula for solid balls. Okay, so I take a solid ball, I take the integral over this ball of the function, and then the value is equal to the value at the center. This we have proven last time. Okay, and you see that this is independent of rho, because if I change the ball, I take a mean value on the larger ball, then the result is always the value at the center. So actually this is independent of rho. Okay? We have, I think, probably we have also written something similar for subsolutions, right? Maybe so if for a subharmonic function, please check in the notes, but I think that if this is subharmonic, then we have less than or equal than an inequality here. Okay, so today there is a theorem. So essentially one would like to say more generally that this condition is equivalent to being harmonic. So for the moment we have proven that if it is harmonic, then the mean value property holds. Now we are interested in seeing whether it is true the opposite implication, namely if I have a continuous function, say, satisfying this for any rho with this property and for any x naught. Is it true that it is harmonic? So this is one of the questions. Let me state. So we will come to this question during the lecture. Now we want to prove a sort of stronger version than this. So let omega be open. Assume that u is a Lipschitz function, and assume that we have the following property here. For any phi, now I explain the symbols, then same thesis, meaning then so let me explain the meaning of the symbols. Lipschitz functions. Do you know what is a Lipschitz function? It's one of the most important classes of functions. So here I have a Lipschitz function with compact support. Okay, this C means compact support. There is something that I have to say. What is this? So there is a big theorem that I don't want to prove. Theorem. If U is Lipschitz, then U is almost everywhere differentiable. So this gradient here is almost everywhere defined, and therefore there are no problems in defining what is the gradient here. Okay, so what does it mean, this theorem? So let us compare this theorem. So this is, say, this is theorem 1, and this is theorem 2. Let us compare theorem 1 and theorem 2. So in the assumptions on theorem 1, we know that this is equal to 0. But more importantly, maybe, there is a strong assumption here, which is this, in theorem 1. On the other hand, we cannot do two derivatives here, you see? We cannot differentiate twice, because this is not allowed. We can differentiate only once, because of this theorem, Rademacher. But we can never write Laplacian of u in this hypothesis, okay? So, on the other hand, so it is clear that now what happens if u is C2, then if I multiply by so this is a test function in this class. So if I multiply this by any test function, it is clear that this is still true. And if I integrate over omega, this is still true. And then if I integrate by parts, I end up with I end up with this function here. With this, I end up with this equality here. Okay. Why I end up with this? Why there are no boundary terms? There are no boundary terms because phi has compact support. Okay? So this means that if this assumption holds, then this assumption holds. Therefore, it is clear that theorem 2, if I prove theorem 2, I prove sort of stronger version than theorem 1. Simply because the assumption of theorem 1 implies the assumption of theorem 2. It is stronger. Okay? So, actually, therefore, theorem 2 is stronger than theorem 1. Let us try to prove it, remembering that we can never write explicitly Laplacian of u, because this is not possible. Okay, so let us take, so these are called test function. You see, this assumption is an infinite number of hypotheses, because for any test, this must be true. And of course, the test has an infinite number. So this assumption actually is an infinite number of assumptions. Now we have to produce, we want to show this, this assertion, and we have to produce a clever choice of test phi. So fix, so proof of theorem 2, fix x naught in omega, rho positive, rho less than the distance rho less the distance from the boundary. And now choose, define phi of x 1/2 rho square minus x minus x naught square. This is a definition, okay? And then actually, sorry, this is not enough. Maximum with 0. So it is, this means, what does it mean, this symbol? It is the max between this number and 0. Simply a symbol. What is this function here? Okay, so this is a sort of object. So if I have x naught here, then this is positive till the distance. So then I take the ball of radius rho centered at x naught. This is rho. Sorry, this is rho. When this is less than rho, then this is positive. And then it becomes negative. But then I take the maximum with 0. Sort of function like this. Okay? So this function, phi, is concentrated on the ball, and then in 0 else. In particular, it has compact support in omega, because the ball is strictly inside omega, and therefore the test function has compact support in omega by this assumption. Is this clear or not? Okay, so phi has compact support, and it is also Lipschitz. It is not C1, of course, but it is Lipschitz. Namely, what what it is true is that the slope here of phi is finite. See? It's sort of object like this. And here the slope is finite. It does not happen in a situation like this, where the slope is infinite. This is not Lipschitz. The slope of the gradient is infinite. But here the gradient, this is a sort of object like this and then truncated. So where I truncate, I am arriving like this and not like this. It is clear by the definition of... Therefore, this function phi is admissible. I can put phi here. So phi is a test, is a so-called test function, admissible test function. So namely, phi is in the class. So why I am taking this phi? Well, first of all, I want to have something concentrated on the ball. Therefore, it is natural to take something which is 0 out of the ball. Next, essentially, this is a radial test function in some sense. It's sort of radial symmetry. So maybe is the most natural choice of phi that one can do. Okay? So now we can, so remember we are proving theorem 2. Therefore, this is our hypothesis. Phi, we have chosen one possible phi. So we can now see what happens when I put phi here. That special phi. Okay? So let me erase. So, inserting this phi in this equality, we have now phi. Another property of these Lipschitz functions is that grad phi, since phi is Lipschitz, this is defined almost everywhere. And moreover, it is 0 out of the ball. Simply because phi is constant. So actually this integral here concentrate on the ball. Dx. Okay? So this is equal to this, and this is 0, therefore we have this. Okay? Now let us see. So let us compute the gradient of phi separately. So the gradient of phi at x is equal to, is the identity, essentially, x minus x naught. And therefore we have the following. Grad u at x, x minus x naught. And I claim that from this equality, I should be able to deduce the assertion. So let us see, what can I do here? Remember, my u is only Lipschitz, so I cannot differentiate it twice. But this is a gradient, so I can integrate by parts, putting the gradient on this side. Okay? So integrating by parts, what's happening? First of all, I have a minus u of x, and then I have the divergence of this vector field. which is the divergence of this vector field. Plus the integral, then I have sorry, let me rewrite for you the divergence formula. So u eta on, say, on an open set is minus divergence of u eta on an open set is the integral over A of grad u scalar product eta plus u divergence of eta, but this is also equal to u eta scalar nu. So I'm using the standard version of the, so now I have this. So now A is the ball, eta is x minus x naught. Therefore, this is equal to minus u divergence of minus this, which is written here, plus u, and then I have the scalar product between x minus x naught and the normal to the ball, outward normal to the ball. Okay. Now, let me compute. So now let me compute the divergence of that vector field. Do you know what is the divergence of this vector field here? It is equal to, so this is equal to minus the divergence of the vector field x minus x naught, the identity, essentially. Remember, the divergence of any vector field is the sum of this. N constant is a constant divergence vector field, and this is equal exactly to the dimension. Okay, minus n integral over b rho of x naught u of x dx. And then I have also that quantity there. Now the outward unit normal to the ball, do you know what is this? Divided by, okay. Okay. This is x minus x naught divided by rho. Okay. So this is the unit normal, and therefore this becomes, I have the scalar product, so this actually becomes, so the scalar product between this and this, it is just rho. Rho. Okay. U of y Is it okay? Now, let us observe that, let us compute now d over d rho separately. Let us compute this. So what happens here? You see there is a volume integral and the surface of u, and the surface integral of u, but multiplied by rho. So now, if I compute this, I have minus n omega n rho to the n plus 1 v rho of x naught u of y dy plus rho to the n, and you already know that so sometimes I write the variable integration x or y is of course the same. Sorry, I can write it x if you want. Is of course the same. Okay, so therefore this is 0. And so minus n, now if I divide it by rho to the n plus 1 over omega n, I find so that this equal to 0 implies that this is equal to 0. Do you see it? Huh? See it? So from this equality equal to 0, it follows that this derivative is equal to 0. Huh? Hence, this means that this quantity is constant, is independent of rho. Okay? Since u is Lipschitz and therefore is continuous, I can let rho go to 0, and therefore u at the center is, so this constant, so let me write it, maybe it is better. So so this is constant, independent of rho. Now u is continuous, therefore the value at the center is equal to the limit of this. Huh? Okay, so we have proven a slightly stronger version. Theorem 2, you see, is slightly stronger than Theorem 1. Now, assume that you want to, so I leave you this as an exercise now. Assume that you want to simulate a similar statement, but for subsolutions. Okay, so for subharmonic functions. So, assume that you want to modify this statement for subsolution. You would like to have as assumption this, but you don't have it. You don't have it because U is just Lipschitz and not C2. So you want to write this in a weak form like this. How can you write this in a weak form? So we have already observed that this is a weak way to write minus Laplace of u equal to 0. Okay? So it is a natural way without writing two derivatives of u. Okay? Do you agree? Now the point is, which is the weak way to write this condition? Say u Lipschitz, now you this condition. Okay. How can I write this in a weak form? exercise. So you see what happens. Let us try to reason as before. Let us multiply by a test function and then integrate by parts. So now, is this true? No. When it is true?
If I is positive.
Okay. Fine. Therefore, we have already the answer to our so because if phi is positive, this is still true. Then when I integrate by parts, I have to put a minus in front of this minus, which becomes a plus, and therefore grad u grad phi less than or equal than 0 for any non-negative phi. This is a weak, so this less than or equal than 0 for any non-negative phi in this class is the weak form, the weak formulation of this condition. Do you agree or not? Huh? So this, okay? No. Do you agree? Yes, okay. Therefore, this is the weak natural form of writing this inequality without never writing two derivatives of u. And so the exercise homework is, this now is the assumption, which is the thesis. Can we deduce that u of x naught, say, is less than or equal than the mean value? Can we deduce this, something like this? Try to do by yourself a similar proof and see what happens. Okay, now another exercise maybe that we do together. So assume that u now is just only continuous, then u satisfy the mean value property in the volume sense. So for any x naught, for any rho, etc., etc. The previous exercise is take an open set omega over M. Take a Lipschitz function u and assume that this is true. So for any Lipschitz test function non-negative, this is less than or equal than 0. Then, of course, you cannot deduce that this is equal to this, but maybe you can deduce that this is less than or equal than this, or larger than or equal. So try to find the right inequality. Try to prove, for instance, this. And what you have to do is exactly the same proof as before. Notice that the previous proof, our test was this, which is non-negative. Therefore, you can make exactly the same proof because this test is allowed. Okay? So you have exactly to follow the previous reasoning. And you can use the same test function because this is inside this. Okay? Yes, so now this is, sorry, here it is for any x naught in omega, for any rho with the distance less than, etc., etc. So write correctly, okay? This is equivalent, so for any for a ball is equivalent to say that u of x naught is equal for any so the mean value property on solid balls is equivalent for a continuous function, is equivalent to the mean value property on the hypersurface, on the boundary of the balls. So this means, I recall that this means 1 over omega n rho to the n by definition. This means 1 over, I think this, hope, the integral, and this is a surface integral, okay? So instead that integrating here and divided by the volume, you integrate just only here and divide by the area. Okay? So actually, if this exercise is true, then we have two possible ways of writing the mean value formula, depending on what you prefer. There is just one point here that you see, for writing this kind of mean value formula, in principle, you just need that u is L1 log. Because you integrate, if your function is locally integrable, then you can integrate locally around the ball. But if your function is in L1 log, this is not defined. Because an L1 log function is defined almost everywhere, and therefore there is no sense of the trace of u on an hypersurface. Has zero Lebesgue measure. The hypersurface has zero Lebesgue measure. Therefore, there is no way to give a meaning of an L1 log function on an hypersurface.
Surface integral is not defined?
What it is not defined is the trace of u on this hypersurface. Because this hypersurface has zero Lebesgue measure, and you can assign whatever value you want remaining inside the L1 log class. So this is not well defined. This integral is not well defined. I mean, if you have an L1 log function in the plane, say, or if you have an L1 log function on the line, you cannot say, and then you have a ball, so this is a ball on the line. Of course, you can integrate u here, but you cannot say which is the value of u here on the boundary or the value of u here on the boundary. This is not defined. You cannot define the values of u on the boundary. You can always change whatever value you want remaining inside the Lebesgue class. This is essentially the difference, and so in order to not to have problems with this definition, we assume at least continuity. Of course, a continuous function leaves a trace on an hypersurface. Okay? So let us see the proof of this exercise. Assume, for instance, that your function satisfies the mean value property in the sense of surfaces. And consider So this is our assumption, and I want to prove this. Okay. So now, therefore, I start from this integral. Okay, and therefore I write it. So this is equal to this. Now it is clear. I make the integral in polar coordinates. Okay, so this is equal to. Now I write this in polar coordinates. So this is equal to the integral from 0 to rho. And then I have, what do I have? I have the integral on the ball of radius r, say, x naught, u of y, dr. dh, this is double integral, so this is dr also. Dr. Okay. Now, our assumption is this. Therefore, this actually is a mean value on a surface of radius r. Therefore, our assumption says that omega n minus 1 r to the n minus 1 u of x naught is equal to u of y d h minus 1y. Okay, so u of x naught is the mean value on this ball, on the surface of this ball, by assumption. So now I can substitute inside this inner integral this. Okay, so this is actually equal to 1 over omega n rho to the n. Then I substitute inside the integral, and this is a constant, and this is also another constant. So omega n minus 1 u of x naught and then I have the integral from 0 to rho to r n minus 1 dr. Hoping that I am doing the correct computation. So what I find so this I can compute. So this is equal to omega n minus 1 divided by omega n. Then I have 1, 0, n, u of x naught. And then this integral is what? Is 1 over n rho to the n. Rho to the n. Okay? Correct? So this seems to be a constant u of x naught. Okay? But this is equal to 1. And therefore, I was starting from the volume. So I have shown that this is equal to this.
Where did you get r from the r over n minus 1?
This?
Yes.
From this. Therefore, we have shown that if you satisfy the mean value formula on surfaces of the balls, then it satisfies the mean value formula inside the balls. Because at the end, we have shown that this is equal to this. Okay. So we have proven such implication. Now let us see the other implication. So assume that for any x naught, for any ball strictly contained in omega, this is true. And then I want to show that then this is true. Do you have suggestions for doing this? So my starting point is this red box is equal to this. So I know that this is true. And I want to find something on the surface, which could be the idea. Remember that we want to pass from a volume integral to a surface integral. There is a way to do this. And the way is to differentiate. So actually, the left-hand side is independent of rho. Therefore, if I differentiate this with respect to rho, it must be 0. Okay? Okay, we have already done this computation, so we have 1 omega n minus n, rho to the n plus 1. The integral will be rho u y dy plus 1 over omega n rho to the n. The integral over boundary will be rho u y. So 0 is equal to this. Okay. Okay, now what do I do? Well, therefore this is equal to this. So let me write it as follows. So minus, I find that the integral over b rho u of y is equal to n over rho times this integral. Okay? And this should be all, because now I divide it by omega n minus 1 rho to the n minus 1. So I have rho to the n, and then I have omega n minus 1. And again, omega n, 1 over omega n is n over, so this is equal. Is it okay? Okay, so it is interesting to have at our disposal, therefore, two possible mean value properties. For continuous function, this is equivalent to this. Okay? Okay, now let us do this. Let us do this following. Okay, this theorem. There's another interesting theorem here in the direction of the question. So theorem 3, let U C omega satisfy the mean value property, MVP. Now, by mean value property is one of the two, okay? Because for continuous functions, they are equivalent. So this is MVP. Then U is so what is the situation for the moment? So UC2 minus Laplace of U equal to 0 implies mean value property. And then even less, U and lip minus Laplace of U equal to 0 in the weak form implies mean value property. Now we are showing that U continuous mean value property implies U C infinity, in particular C2. And then we will prove that this will imply that actually U is harmonic in the classical sense. Okay? So let us see the proof of this theorem. So let us choose, let me denote it by eta epsilon standard mollifiers. What does it mean, standard? It means that they are radially symmetric. It means that they are non-negative. It means that they are C infinity. It means that they are the support of eta epsilon is contained in B epsilon 0. For instance, the usual way is maybe eta of x equal maybe E minus x squared if x less than or equal than 1 and 0 else. Maybe let me call this eta tilde and then eta of x 1 over the integral of eta tilde Okay, so it is simply a smooth infinity function. And then there is, yes, there is eta epsilon of x, epsilon to the minus x over epsilon. Okay? So that we always have that, we always do this normalization. Okay? So standard sequence of mollifiers. Okay, let us consider the function u epsilon for any x in omega such that the distance of x from the boundary of omega is larger than epsilon. So I have omega here. And then I have all points. So epsilon is very small, actually. But so this is, so say this is epsilon. So I take a point here, the distance of which from the boundary is larger than epsilon. So now so let me call this maybe this set omega epsilon minus, a little bit smaller than omega of the factor epsilon. Okay? So for any, namely for any x in omega minus epsilon, I can consider the following: the convolution of u with eta epsilon. U convol. Okay. So this is the integral over, let me use the same symbols, u of y, eta epsilon x minus y dy. Why, so this is the definition of convolution. Why I'm taking x in this set? Well, because it is obvious that if I take x here, for instance, then I am involving values of, so I'm actually integrating. So the convolution is like integrating in a small ball centered x of radius epsilon. So I go outside omega and u is not defined anymore. Okay? Therefore, in order to have a meaning of this quantity, I need to take x a little bit inside. Otherwise, this integral is actually inside the ball of radius x, ball centered x of radius epsilon. And therefore, I have problems for u. So this is why. But on the other hand, for any x here, this is well defined. Okay? Okay. So u of x is equal to the integral over omega of u of y eta epsilon x minus y dy. So now this is equal to what? Now let me recall who is eta epsilon. So eta epsilon. So at the end I want to show that at the end after some I want to show that this is equal to u. So if I am able to show that u of epsilon is equal to u for any x in this smaller set, then what I have proven is that u is infinity inside this smaller set. Because it is well known that this is infinity. This is known. Okay? So if I prove, of course, that u epsilon is equal to u, then I have that u is C infinity in this set. But then I can always take epsilon smaller and smaller. So at the end, at any interior point, if I take epsilon small enough, u will be equal to u epsilon at that point, the neighborhood of that point, and u is infinity inside in the interior. Okay? And therefore, it is enough to show that this equality holds. So let me compute this. So this is equal to, this is concentrated, the support of this is just inside the ball of radius epsilon centered at x, therefore this is equal to u of y eta epsilon of x minus y, now it is radial, dy, okay? So this is just an integral concentrated here. Eta epsilon is radial, okay. Therefore, now, what is eta epsilon? Remember that eta epsilon of z is epsilon to the minus n eta of z over epsilon. This is the definition. So we can construct just by homotopy, starting from just only one and we have this. Okay. Now what do I do? So I go here now. Now I integrate in polar coordinates. So that is equal to epsilon to the minus n, integral from 0 to epsilon. Then integral over the boundary, let me call this r, maybe. We call this r, yes. And then what do I have? I have u of y dy, and then I have eta of x minus y. Actually, now x minus y is equal to r. Therefore, I just have eta of r divided by epsilon. And then I have u of y dh n minus y. So I simply write this integral as the integral of 0 epsilon integral same quantity dh n minus y. Yeah. Now I observe that when y is on the boundary of this ball, this difference is actually r. So since it is r, is independent of y, and therefore I can put it outside the inner integral. Okay? Now I finally use, so for the moment I have just used the definition of convolution. I have used that the kernel is radially symmetric and supported in the ball. That's what I have used. Now I use the mean value property. Because now my assumption is that assume that U is continuous, satisfy the mean value property. Now I use it in the surface form. I know that it is equivalent the volume and the surface form. Now I use it I see it from the proof. It is for me convenient to use it in the surface form. Therefore I know what is this. Okay? So this is equal to r to the n minus 1 omega n minus 1 u of x. Okay? So I can substitute. So what? Ah, sorry. Thank you. Thanks. So I can therefore so this is equal to this. No, with the dr. With the dr. Okay. Sorry, without the dr. Thank you. So now I can substitute, and therefore what do I have? So let me go maybe here. So I use now the mean value property in the surface version. U is continuous by assumption, so I can do. So I find epsilon to the minus n, omega n minus 1, epsilon to the minus n, u of x, the integral from 0 to epsilon, r to the n minus 1, eta over epsilon, dr. Okay. Now, homework by the property normalization property of eta. We know that we know what do we know? We know that the integral omega n on the ball of radius epsilon centered at 0, say, of eta z dz, eta epsilon z dz, we know that this is equal to 1. Remember, we always have this, eta equal to 1, and also this. So I claim that this actually is equal to 1. Check this at home. If this is true, then this is equal to u of x. And this is true by our properties of normalization, this session. Okay. Now I have erased my small scheme, unfortunately. So let us now show that the answer to our initial question. So theorem, let me call this theorem 3, maybe. Theorem 3. Okay, assume that U is C2. So assume that U is continuous and U satisfies mean value property. Then U is harmonic. And this statement is correct in the sense that in principle U is only continuous, and therefore we cannot write Laplacian. But we know that if U is continuous and satisfies the mean value property, it is infinity. So let me just add here. Okay. Actually, there is also a remark that should be made. Let me write it here. That it is interesting remark. We have already proven this remark, actually. If U is C2 and U is harmonic, then U is infinity. This is actually very interesting. So this is a regularity, first example of regularity theorem. So regularity theory is maybe the most difficult part of partial differential equations. It asserts that, like this, I mean, you have a function satisfying a PDE involving only two derivatives. So it is rather surprising that if you look at this statement, then actually U is infinity. This is really surprising. And this is, I mean, the content of regularity theory in PDEs. The most difficult part in the theory is exactly this. Okay? And why is this true? Because we know that, the proof we know how to do this. U satisfies we know that if it is harmonic, it satisfies the mean value property, and if it satisfies the mean value property, it is infinity. So at the end, we have this interesting, maybe theorem more than remark. Theorem. Theorem. It's a theorem. Okay? First surprise. Okay. So now, so this says, if we prove this says that actually being harmonic or satisfying the mean value property is equivalent for continuous functions. Okay? Okay, let me introduce, for proving this result, let me introduce the function phi of r, that is the mean value over the solid, no, maybe this again, u of y dy. Let me compute this. Now let me define this for any r, for any x, for a point x in omega and r sufficiently small. And therefore now we want to compute phi prime of r. Now, to compute phi prime of r, maybe it is better to, you see, there is a difficulty here in computing phi prime of r, because the dependence on r is on the surface. So the idea is, in order to overcome this problem here, is instead of integrating on this, make a change of variable and integrate it on the ball of radius 1. So that r goes inside here.
Because of the value theorem, it is equal to root x, and that's why it's equal to 0.
Yeah. But still, let me compute this. Okay? So I rewrite this as follows. So I rewrite this as follows. B prime. So let me do this. U of x plus r z dHn minus 1 z. So we know that this derivative must be 0. Okay? But let me write it as follows. So let me see if I'm correct. So if z is in the boundary of unit ball, then rz is in the boundary of the ball of radius r. It's okay. And then I am also translating the center. Okay? Now, let me compute phi prime of r, which is 0 at the end. So this is equal Now, there is no r anymore, neither here nor dividing by the unit volume, unit surface area. So this is equal to scalar product of grad u. I already know that u is infinity, so I can differentiate. I am differentiating with respect to r, therefore this is scalar product with z, dhn minus 1 z. Okay? And now I come back to the previous integral in the variable r. So I come back to the boundary of BR x grad u y. And now z is z is this, and therefore it is x minus y dHn minus y. Mistake, y minus x. Okay, so I go back and forth from the integral of the ball of radius r centered at x on the translated ball centered at the origin of radius 1. So I do this first computation because for me it is easier to compute the derivative with respect to r. Now I come back to this. And now what do I do? This is, you see, what is this? It is the scalar product of the gradient of u with the unit normal, outward unit normal on the ball. Which we know to be equal. Now we have integration by parts. Okay, so this is equal, so let me divide it by the correct quantity, r to the n minus 1. And then I have now solid ball. Okay, so this is equal to 0 because phi, we know by the mean value property, is independent of r. So phi prime is 0. Okay. Fine. Okay. So this is equal to 0. And therefore now I think that the proof should be almost concluded, because since assumed by contradiction now, so assume now that by contradiction that u is not harmonic. So therefore there is a point x where this Laplacian is non-zero. Therefore, u is continuous. Actually, it is C2. So assume, for instance, that this is positive at a point. Therefore, by continuity, there is a small ball where the Laplacian is positive. Which contradicts this. therefore we have this interesting result that actually, so this is more difficult, you see, but we have a sort of characterization of harmonicity even for continuous function. If you have a continuous function which satisfies the mean value property, then it is harmonic in the classical sense. Maybe I can leave you another homework, not so difficult, perhaps. Home. Consider the ball of radius ρ centered at the origin R2. So let's call this omega. Okay. Take a function phi of theta equal cosine of n theta. 0 to pi, say. And then find an harmonic extension so phi of theta is essentially defined on the boundary of the ball, unit ball. Find an harmonic extension of phi in omega. What does it mean? That is, equivalently, find an holomorphic function in the ball such that the restriction of its real part on the boundary, so take for the ball of radius 1 for simplicity. Okay, such that find an holomorphic function in the ball such that the restriction, an holomorphic function f, such that the restriction of the real part of f boundary of omega is equal to phi. This means that you are solving in the ball u equal phi boundary of the ball. And the same can be done also for sinus and theta. One of the two. So it is not difficult, not so difficult to find if an holomorphic function having this is not difficult, right? Can you imagine what it is? Theta is in.
Maybe it's better to take the theta modulus of theta equal to 1 and theta is complex number?
No, actually, yeah. Theta yes, theta is a complex number of modulus 1. Okay. Okay, theta is a complex number of modulus 1. But it is, I mean, if you take f of z, z to the n, this is holomorphic, and let us write it as, so if I write rho with now theta, the argument, so this is equal to theta Now if I take the real part and I restrict it on the boundary of the sphere of the circle on the disk of radius 1, this is equal exactly to the cosine of n theta. So in this sense, theta, I mean, is just the argument of the complex number. So it's in between 0 and 2 pi. Just the, so maybe we can keep it like this. So this is the answer to, well, once you have this, do this also for the sinus, then for the sum of 2 you can do, because this is a linear function, it gives you some example of harmonic function on the ball. Okay.